Hi, this is Dan Petrock, and this video is to help students learn how to use the simulation-based methods for inference with a mean. This gets a little tricky. I think it's one of the more difficult things we do in this intro course. We're using the data for the Colorado Rockies home run data to test to see if they hit home runs farther than the average home run. So in bootstrapping, we are given a small sample and we're trying to make an inference to the population. Now, this is very powerful. We don't need as many assumptions to use bootstrapping. We don't need to, know normality. We get large. We can do this thousands of times, and it narrows our error and our intervals. If we do confidence intervals, and when we calculate our p-values, they're more accurate too. So it's a very powerful thing, but it takes a little more work on StatCrunch. So I'm going to show you how to do that. In this particular one, you can see the null hypothesis is the home run in Major League is 397.6 feet. The alternative is greater than. I'm going to go ahead and just go through this particular one. And also, because sometimes there's two-tailed tests, I will go back and actually make this a not equal as well, so you can see both ways to use StatCrunch and the histogram and all those good things. So if we go ahead and open the data in StatCrunch, the first thing you want to do is find the mean of the sample, because what we need to do is recalibrate this sample mean to be the equivalent of the population mean or the understood population mean. So if we're going to use this data to model what the population looks like, we can't model it with the average to be out here at 410.42. We need to make it over here at 397.6. So to find the mean, probably the easiest way is to go summary stats, columns, var1, compute. All right. So that's how we get the mean of 410.42. And I think it says around 2 decimals. So we're just going to use that. Now, if I take, I want to adjust this down. So the way I look at it is if we drew a normal distribution and put the middle at 397.6, we could see 410.42 to be to the right. The question is, how far right is it? Well, if we just, open up a new tab or whatever, a calculator, and put 410 point, what was it again? Oops, I'm sorry. Oops, I'm sorry. I open it, here we go. 410.42 minus 397.6. So it is 12.82 higher than what we would want. So we need to adjust it down. Now, the easiest way, I think, to adjust this down is to go ahead and subtract that number from both. Here we go. Cool. So again, I'm just going to stay in StatCrunch. All right. So what I'd like to do is move. Now the videos they show on our thing kind of give you kind of a lengthy formula that I don't think anybody remembers. So the way I teach my students is to do this. All right. I found this. I need to move this down, either greater than, I need to move it left or right or whatever. In this case, we need to move it down 12.82. So I just go data, compute expression. And the easiest way to think about this when we're going to build this is just take var1, add column, minus 12.82. I'm a big fan of actually figuring out what that number is, because it's easier for students to think about, oh, I'm going to either move it down or I'm going to either add or subtract from it. And I just hit OK and compute. So now we have this, what we call this adjusted sample that we're going to do our bootstrapping from. So let's just go ahead and do that. So go to applets, resampling, bootstrap a statistic, and then we are going to find our samples in this adjusted area. We're doing it for the mean. It gave us a fixed seed here of, let's see here, 12931. 12931. So we've got this, and we compute, and it says to do 2,000. So we go bam, Bam. So we've done 2,000 resamplings of 12 home runs, and we found the mean of all 2,000 of those, and this is a plot of all 2,000 of those means. So now we're saying, okay, what's the probability that we would find one that is 410.42 or more? So we're trying to find out what's greater than. A good way to do this, and to use the histogram method, which is awesome because then you can see it, hit the Analyze button. And now we put all 2,000 of those sample means in StatCrunch. And what we'd like to do is make a histogram of those. So go Graph, Histogram, Bootstrapped, and we want to do this and also click percent because it'll make percent dividers and hit Compute. Now we can drag these dividers wherever we want, okay? Now the problem is I want to put it at 410.42. Well, I can't, that's hard for me to do. So I can, if you go right there, it gives you the number, but if I double click it, I'll make this bigger. There we go. Let's make this. Double click it, you can type in 410.42, hit Compute, there it is. So the p-value, the probability that you would get a random sample of home runs greater than 410.42 is only 0.4% or 0.004. That is super rare, which tells me the home runs at Coors Field are longer because the probability of getting that by random chance is rare. Now, could we be wrong? We could say yes, reject the null. Since the p is low, the null must go, reject the null, and say yes, there is statistically significant evidence that the home runs at Coors Field are longer. If we were wrong, that would be a type 1 error. If we reject the null, but it really wasn't longer, that's called a type 1 error. And if we did a test and we failed to reject, but we should have, like we said, nope, they're not longer, but they really were, that's called a type 2 error. So just want to kind of throw that in. So 0.4%. So if we go down here, let's see here. But it looks like they got, oh, got to round that right. Yeah, 0.4. I wonder if they carried more, but it may have a tolerance of 0.01 as well. So, and a lot of times they're going to ask you, if you repeated this test like 1,000 times, 10 times, you have 5 out of 1,000 that would have that. But anyway, since p-value is definitely less than 0.05, reject, there's sufficient evidence that they are longer. So that's kind of how to do all of that. But here's also the tricky part. If we know that this sample is 12.82 above normal, if it was a two-tailed test, for instance, if this said not equal to, we'd also want to look below. So if I take 410.42 and if I take 397.6, the population mean, and I subtract off 12.0 minus 12.82, that puts me at 384.78. So if I wanted to make this a two-tailed test, I've got my one here at 410.42, and I could click the other one, double click here, and put that one at 384.78 and hit Compute. And that is also at that's at 0.004. So you could say the two-tailed test, you would add these two. Sometimes they're the same, sometimes they're not, based on how your simulation ran. So this would be 0.008 would be the p-value for that one. Still would reject. There is sufficient evidence. So in this context, it doesn't make any sense to look both ways. It definitely said greater than. Sometimes the context would say, is it different? And then you'd have to do two-tailed. The distance from the middle to the sample, you have to go both ways the same amount. So that's about the trickiest one they have in the course, I think. So I thought I'd show you how to do that, do it with the histogram, how to adjust these. You could even do this with confidence intervals. Let's say we want to make a confidence interval for this. You could say, I want a 95% confidence interval. You could just change the percentage to 2.5%. And then you could go over here and double click that and put 2.5%. We could use simulation-based methods to find the 95% confidence interval, hit compute. And now we'd say 95% are between 387.9 and 407.138. Again, 410 is way outside of this. So this, again, kind of confirms our sample is from course field is definitely not a normal one. So hope this video helps, and shoot me any questions if you have any.